Namaskar. In this video, we will discuss logistic regression. My name is Partha Majumdar. I use data sciences in many of my works, which I conduct for business and for academics. To understand logistic regression, in this video, I will use Excel. While Excel can be used for solving logistic regression problems on small data sets, however, when it comes to industry-grade problems, we will require some kind of programming language like R or Python or Scala, Octave, etc. So let's get started. Before discussing logistic regression, let us discuss linear regression briefly. We will require many of the concepts here to understand logistic regression. Now take an example where we have the sides of a right angle triangle and also we have the values of the hypotenuse. Now we can get this data quite easily because if we draw some right angle triangles on a sheet of paper and then use a scale to measure the two different sides and the hypotenuse, we can create this data. Now we have some intuition that there may be a relationship between the squares of the sides and the hypotenuse. So we have this intuition. How this intuition came about, we will not get into that right now. However, we have an intuition that there is a relationship between the squares of the side instead of just the sides and the hypotenuse itself. So what we do is that we take the squares of the side. So this is nothing but x1 square and this is nothing but x2 square and this is y square. So we will call it capital X1, capital X2 and capital Y. So we have this data now. This is our feature engineered data. Now we will try to do a linear regression here where we will see if we can find a relationship between these two independent variables and this as the target variable. So what we really want is to find a equation of the form, y is capital Y is equal to beta 0 plus beta 1 capital X1 plus beta 2 capital X2. So this is what we want to find. Now say for example, we have a simplified situation where we just have one independent variable, that is X2, and one dependent variable, that is Y. So in this case, what we can do is that we can draw a scatter plot across these two variables. So we can do it like this. We can draw a simple scatter plot. So I get this plot. Now on this plot, what I can do is I basically now here what we have is we have only two variables, that is X2 and Y. So what we want here is that we want to find a line between these points such that it represents it can be used for prediction of the values of Y based on the values of X2. Now what we do is, so here in this case we want an equation of the form capital Y is equal to beta 0 plus beta 1 X2. So this is the line which we want to form, and we do not know the values of beta 0 and beta 1. That is what we want to find out. So what we will do is we will start with some arbitrary value of beta 0 and beta 1 and we will draw a line. So we will assume that this line best represents the data and can be used for prediction. After we draw this arbitrary line, what we will do is that we will find the difference. So for this value of X2, this is the predicted value of Y. However, the actual value of Y is here. So there is a difference. So what we do is that, supposing we will call this as Y hat, and we know that this is Y. So what we want to do is that we want to find Y minus Y hat. Now the Y minus Y hat, you notice that sometimes it is negative and sometimes it is positive. So since we have negative and positive values and they may cancel each other, so we will take the square of this so that this is always positive. And when we have this quantity, so this is called the square of error. Why is the square of error? Because This is the error. Y minus y hat is the error, and we square it, so we'll get the square of error. Now, if we take all the square of errors, that is this one, this one, this one, this one, and so and so, that then we sum it up, we will get the sum of squares of error. And if we take the mean of this, we divide by the number of data points we have, that n is in this case equal to 1, 2, 3, 4, 5, 6, 7. So we have 7 data points. So if we divide by the mean, we will get something known as the mean square error. Now our purpose is to minimize this mean square error, right? So this mean square error is nothing in this case, which we will refer to this as the loss function. The purpose of our optimization is that we must minimize the loss function. So minimize loss. So having understood this on a two-dimensional plane, we can extend this idea. I will clear out this writing right now. I would clear out this writing. And also I will clear out this chart. Okay, so now when we consider both the variables x1 and x2, then what we will require is we will require a coefficient b0, that is the intercept. So this is the intercept. And b1 and b2, b1 for x1 and b2 for x2. So these two variables put together, this is the slope, right? So now we have to find the values of b0, b1 and b2 such that we can find a linear relationship between x1, x2 and y. That is capital X1, capital X2 and y. So what we do is that we assume some value of b0, b1, b2. I have given some arbitrary value of b0, b1, b2. Based on this arbitrary value, we can try to figure out what is y hat. Y hat is the predicted value of y. So predicted value of y will be nothing but, this is b0, I fix it, plus b1, I fix this as well, multiplied by x1 plus b2 multiplied by x2. So this is my predicted value of y, which we are calling y hat. So I can copy this for all the different data points. So I get these as the predicted value of y. Now we already know the actual value of y, which is here, which is the square of the observed value of y of the hypotenuse that we have noticed. So there is a difference between the actual value of y and the predicted value of y. This difference is nothing but the error. So I can find the error by subtracting capital y hat from capital Y. So I get the error. So I can calculate it for all the data points. Now notice that the error is sometimes positive, and in this case error is always negative right now. So but it can be sometimes positive and sometimes negative. So in that case what we do is that we take the square of the error. So we will take the square of the error. So I calculate the square of the error. So I get this. And then I calculate the mean square error, which is nothing but the loss function. So mean square error is the average of all the square of the errors. So I have got my mean square error. Now my purpose is that I have to minimize the loss function. So I have to minimize the mean square error. So normally what we will do is that we will use gradient descent algorithm. So in gradient descent algorithm, what we have is that we will have some kind of a curve, and we have to find what is this point of minimum. So this is the place where we'll get the optimum solution. But we do not know this. So we will start at any arbitrary point. Let's say we start from here, and then we will change the values of this beta 0, beta 1 and beta 2, and we will do that in small steps. So after changing, maybe I will move from here to here, and then after changing that again, I will move from here. How we are changing is by something known as the learning rate. So we will keep learning based on the learning rate, and as we change the learning rate, the values of the loss function will keep reducing, and we may move towards the minimum which we are seeking to move. So we can move like this, then we can move here, and ultimately we can come here. So this is possible. So I may do this. Now in Excel, it is not possible for me to simulate gradient descent. So what I will do is I will use a simpler technique. I will use the solver, which is going to simulate the same as what a gradient descent will do in a simple case. So in the solver, I will say that my objective function is to minimize this. So I'll say minimize this by changing the values of this beta 0, beta 1, and beta 2. So once I do this, I can say solve this equation now. So I say solve, and let's see what it does. So it has reached some solution. So it has got this solution where it says beta 0 needs to be 0, beta 1 needs to be 1.00 something, and beta 2 needs to be 0.98 something. So it has found, and it has found the minimum mean square error in this particular case. Now once I've done this, I can test my model by trying some new values. Let's say I put x1 as equal to 3 and x2 as equal to 4. So in this case, capital X1 will become 9 and capital X2 will become 16. Now I can calculate y hat. This is equal to beta 0. I fix this once again, plus beta 1 into x1 plus beta 2 into x2. So this is my y hat, but we know that y hat is the square of the hypotenuse. So we will have to calculate the hypotenuse as the square root of this value. So the predicted value of y is 4.98. Now we can see that the actual value of y should have been 5, because I can find this out. I know the Pythagoras theorem. Pythagoras theorem says that x square plus y square is equal to hypotenuse square. That is a square plus b square is equal to c square. So here 5 square plus 4 square is equal to 25. Square root of 25 is 5. Now my predicted value is pretty close to the actual value. So it is a fairly good model. I can try with another example. Let's say we try with 4 and 7. So 4 and 7, I get x1 square and x2 square like this. I can copy y hat. So I get y hat like this. Based on this, my predicted y is 8.023, whereas the actual y is 8.026. So this way you can try other values. You'll find that this model is fairly good. So let us understand a few important things that we have discussed. That is, we may require to sometimes engineer features. That is number one. Then we have to have these coefficients, which we have to estimate in a linear model. The coefficients, we start with the arbitrary value, and then we find a mechanism to we create a loss function. The loss function creation is very important, and we will always try to minimize the loss function. So normally the minimization is taking place by gradient descent, but in this case we are using Excel. So I used solver. So once the loss function is minimized, I get the optimized value of the coefficients, that is beta 0, beta 1, and beta 2, using which I can make predictions. So after this discussion, we are ready to now move to logistic regression. So let's do that. So having understood linear regression and the essential components for making a model, now let us step into logistic regression. So here what we have is a data regarding some people whose age is given. So this column contains the age and this column contains the salary. And this column contains the y variable, which is the target variable, which is a decision whether they will buy a particular product or not. So this is a situation what we have created. This data is arbitrary. Anyway, this is a practical situation where we have the person's age and salary, and we have a decision he will make whether to buy a particular product or not. Now, the first thing we notice is that the scales of these two data, age and salary, are quite different. So this is a problem, because in this case, since this value of salaries are very high, they will be very dominant on the model if we create it right on this data. So under this circumstance, we will scale the data. One way to scale the data is standardization. Standardization, what we do is that in standardization, what we do is we find a z value. The z value is nothing but equal to x minus the mean divided by sigma. So we need to first find the mean and sigma. So which is quite simple. So this week I can find the mean here by saying average of this data, and I can find the standard deviation by saying stdev of this data. So I have found this. I can do the same for the salary column also. I can just copy this and paste it here. So now I have got the mean and standard deviation of age and salary. So using this, I can normalize the data. So for normalizing this data, I can say this is x minus the mean. I will only fix the row divided by standard deviation. So again, I will only fix the row. So once I do this, I can copy this across. So now I have got the normalized data. This normalized data I can utilize for creating the model. So you can see that the normalized data, by virtue of standardization, we will get the data in the range of minus 3 to plus 3. The data can be minus infinity to plus infinity, but 99% data or a little more than that will be between minus 3 to plus 3. Plus 3. So because normal curve will be something like this, where 99% of the data will be between minus 3 standard deviations and plus 3 standard deviations. So now we have got the normalized data. Now what we do is that in logistic regression, like we use a different function. In this case, the function is called the sigmoid function. So the sigmoid function, what we do is that we take, the sigmoid function has got the quality that for every value of x, the y will always be a value between 0 and 1. So this is 1. So y will always be a value between 0 and 1. So what is the sigmoid function? The sigmoid function is fx is equal to 1 divided by 1 plus e to the power x. E is the exponential, e to the power minus x. So this is a sigmoid function. Sigmoid function. Now in this case, what we have is we have two variables, two independent variables, x1 and x2. So we will have to find three coefficients. That is, this is the intercept b0, and for x1 b1 and for x2 b2. So basically what we have is that we have to find a z which is equal to beta 0 or b0, like I have written it to avoid the Greek alphabets, plus beta 1 x1 plus beta 2 x2. Once I have found this z, then I can find the sigmoid function. So I can say sigmoid function of z. So this will be equal to 1 by 1 plus e to the power minus z. So in other terms, we can say that this is equal to 1 by 1 plus e to the power minus beta 0 plus beta 1 x 1 plus beta 2 x 2. So now we have understood this. Let's find these values. So first I find the value of z. So z is nothing but, this is beta 0. I have taken some arbitrary values of beta, just like I did in the case of linear regression, because I do not know what is the actual value of beta. So this is beta 0 plus beta 1 into x1. So I take the normalized value plus beta 2. This is beta 2 into x2. So I can find this. So I can find this for all the data points. So the values of z are now available. Now, based on this value of z, I can find the sigmoid. The sigmoid is nothing but 1 divided by 1 plus exponential of minus z. So I found this. So I calculated for all the data points. Now I told you the sigmoid can take a value between 0 and 1. However, we want a decision in this logistic regression case regarding whether the person will buy or not. So that means I have to have two values, a binary value, 0 and 1. So in this sigmoid function, what we can do is that we can set a threshold that if the value of the sigmoid is greater than, let's say the threshold I have said initially is 0.6. So if the value of the sigmoid is greater than 0.6, that is this area, I will say that the predicted value is 1. If it is less than 0.6, I will say the predicted value is 0. So that is what I set a threshold. So I can put a function here which says if sigmoid is greater than threshold, then 1, else 0. So I can do that. So it has found the y hat. This is the predicted value of y. So you can notice that by default it is making mistakes in two cases. That is, here it should have been 0, it is predicting as 1. And here also it should have been 0, it is predicting as 1. So it is making some mistakes, but now we have got arbitrary values of beta 0, beta 1 and beta 2. So what we require is to optimize the values of beta 0, beta 1 and beta 2. And we can do that by finding a loss function and minimizing the loss function. In the case of logistic regression, the loss function is like this: minus y into natural log of sigmoid minus 1 minus y into natural log of 1 minus sigmoid. The sigmoid is z. This is sigmoid, the sigma. So let me just correct this. Sigma. Okay. So this is what I want to find. So I can plant this formula here. So this I can say minus of y. So y is here into natural log of the sigmoid minus 1 minus y into natural log of 1 minus sigmoid. So now I have got my loss function. So I will copy my loss function across all the data points. So I have got my loss function, and I can find the sum of the loss function. That is, this sum of the loss, since this loss function is containing a log, so we can say that the loss, we can say this is a log loss function, we call it. And by summing up, this is nothing but the sum of all the losses. So this is the sum of all the losses. So I get the log loss. Now my purpose is that the loss function has to be minimized, right? So I have to minimize this value of log loss. So if I can do that, I will get the value of my beta 0, beta 1 and beta 2. Now let us see, we have got the values of y hat and y. So I can find y minus y hat. This is nothing but y minus y hat. I can do this. Now, if the difference between y and y hat is 0, that means to say that the prediction is correct. So I can count the number of zeros in this prediction, in this calculation. If number of zeros, the count of number of zeros tells me the number of correct predictions. So by default, by taking arbitrary values of beta 0, beta 1 and beta 2, I'm getting correct predictions in 5 cases and wrong predictions in 2 cases. So my accuracy is equal to 71%. Accuracy is nothing but number of correct predictions by total number of data points. So number of correct predictions is here, and total number of data points, if I count all these values and count the number of values here, that gives me total number of predictions. So this is my accuracy, 71%. Now my purpose is that I have to minimize the log loss and to obtain the optimum values for beta 0, beta 1 and beta 2. I can just try by chance. I can try these values. I noted down because I was testing. If I put these values and then check, you notice that it is giving me again 5 correct answers and 2 wrong answers. So I can start with this also, or I can just revert back to my initial setting of 0.1. Now I set up my solver. I will just remove all this writing so that it is clear. Just give me a moment. Okay, so now let us set up the solver. So I go to data solver. So here I have to minimize the loss function. So minimize this by changing the values of beta 0, beta 1 and beta 2, and let us solve. Now it starts solving. Why? Yeah, it has done something. Now what has happened is that you notice that it has found very high values of beta 0, beta 1 and beta 2. Now in logarithmic, in logistic regression, beta 0, beta 1, beta 2 should be very small. It is very sensitive to the coefficients. Now in this case, we have got very large values. So what has happened? Actually, what has happened is that in this case, see, we are doing gradient descent. So we had this function, and our objective was to find this minima. So we started at some point, and we kept on learning, and we kept on moving towards the minima. So in some cases, it can happen, like in this case, it has happened that it has overshot the minima, and then it has proceeded in the wrong direction, and it is now not able to find the minima at all. It is moving in some direction, and it has found some arbitrary values of the gradient. So this is a situation. This situation is typically called gradient explosion, where the gradient has exploded to a very high value. That means to say the model has not learned appropriately, and that is why we are getting very wrong figures. Gradient explosion. So this can happen in many learning situations. This can happen that we do not find the optimum value by applying the model. So in this case, we have a technique where we can bind the values of beta 0, beta 1 and beta 2 within a certain range. Now that is called, when we try to bind the values of beta 0, beta 1 and beta 2 in certain range, that is called regularization. So let us see what happens with regularization. So in regularization, what I will do is that let me clean this once again. So now we are in regularization. So let me just, yeah. So here, let me just correct this formula. Here also there's a mistake. So this is got to be sigma. This has got to be sigma. Okay. So I have the same data. I have exactly everything the same. Now what I will do is that in regularization, I want to bind the values of beta 1 and beta 2. What I will do is that I will say that this is beta 1 and this is beta 2. I will bind the values of this within a circle. So what I do is that I use regularization where I am setting some lambda. This is a hyperparameter, and you see here I am finding lambda into beta 1 square plus beta 2 square. So this beta 1 and beta 2, I am binding it within a particular circle. The values cannot go outside the circle. And what I do is that I change my objective function. I use the log loss what I've calculated and add the regularization to that. So this is the log loss plus regularization. Now I will try to minimize the objective function, which is the log loss plus regularization. So let us see what happens. So I open the solver once again. So here my objective function is now changed to this, that is log loss plus regularization, and I will change the values again of beta 0, beta 1 and beta 2. And now let me solve the problem. So let us wait for the solver to work. So the solver is now calculating. It has found some answer. And now you notice that it has found the answer, and the betas 0, beta 1 and beta 2 are within a very small range. So it has found this, and also we notice that the model is now correctly finding the y hat in all the cases. So here we have accuracy of 100%. So you notice that we have calculated the new prediction to 100%. So we have found a model which is working very well. Now we can use this model just like we did in the case of linear regression to make predictions. So what we can do is that we can try to predict. So let me say predictions. In this case, I take the age and salary, and let's say the age is 37 and the salary is 41,000. In this case, I can find the y hat. How to find the y hat? Y hat is nothing but beta 0, not beta 0. It is, first I have to find the sigmoid. So z first, then sigmoid, and then y hat. So z is nothing but equal to beta 0 plus, we fix this, beta 1 into x1 plus beta 2 into x2. So I found z. Now this is a very large value. Oh, sorry, I had to normalize this. I did not, I forgot to normalize this, so that I should do. Let us take this whole thing down a little bit. Yeah, so first let me move this slightly this side. And here I say x1 norm and x2 norm. So x1 norm is nothing but x minus the mean divided by sigma. So here I anchor this and anchor this. So I get this. So I can find the x2 norm also. So I found this. Now I find z. So I replace this B25 with this and C25 with this. So now I have found z. Next I can find sigma. Sigma is equal to 1 divided by 1 plus exponent of minus z. So I found this, and then I can find y hat is equal to if sigmoid is greater than threshold, then 1 else 0. So this says that if this is the case where the age is 37 and the salary is 41,000, this person will buy the product. So you can make predictions like this. So this has now become a classification model where it is a binary classification where it is to be able to take decision between two outputs, whether the person will buy or not buy. That is 0 and 1. So far we saw that we had a situation where the logistic regression was having a gradient explosion problem, and we solved it using regularization. Lastly, let us see how we can plot this so that we can get the decision boundaries. So now what I have done here is that I have taken the values of x1 and x2 and I have plotted a scatter plot. So these values are coming here. These blue dots you can notice are the values of the scatter plot between x1 and x2. Now what I will do is that I have got beta 0, beta 1 and beta 2 arbitrary values right now. I can get the optimized value. I know that. I'm using regularization. And then I take some values of D1 and D2. This is for decision boundary. So D1 I take values from -2 to +2. And I calculate D2 as betas. This is equal to beta 0 plus beta 1 into D1 divided by beta 2. So let me fix these values of beta. So this is $, $, $, and this is $, $. So if I calculate this D2 in this manner, so notice that I'm getting a line like this. Did I calculate correctly? Yes, I did. Now what I do is that let me optimize this function to get the optimum values of beta 0 and beta 1 and beta 2. So here my objective function is this one, that is log loss plus regularization, and I will change the values of beta 1, beta 2 and beta 0, and let me do the calculation. So it is solving this linear programming problem. This is a good alternative for now. It gives me a decision boundary like this. This is not such a good decision boundary. The decision, oh, I made a mistake actually. This should have been a minus. This should have been a minus. That is the reason why I am getting a mistake. Now you notice that the decision boundary, it is clearly demarcating that these 4 points are on this side and these 4 points are on this side. So this represents the values where the person will make a purchase, and this represents the values where the person will not make a purchase. So I can see that I have clearly found a boundary that if the data points are on this side of this particular line, then the persons will make a purchase decision, and if the data points on this side of the line, the person will not make a decision to purchase the product. Okay, so that ends our discussion. Thank you for listening. I hope you enjoyed the presentation as much as I did. Keep watching for other presentations on data sciences. Goodbye.